In 2017, humanity encountered something that challenged our understanding of physics and sparked one of the most heated scientific debates of the modern era. What if our first confirmed interstellar visitor wasn't just a rock from space, but something far more extraordinary? When the universe sent us a message. Picture this. A cigar-shaped object, perhaps as long as 10 football fields, hurtling through our solar system at speeds that would make even our fastest spacecraft seem sluggish. This wasn't supposed to happen. For centuries, astronomers had theorized about visitors from other star systems. But when one actually arrived, it brought with it mysteries that would divide the scientific community and capture the world's imagination. On October 19, 2017, the Haleakala Observatory in Hawaii detected what initially appeared to be just another space rock. The object received the mundane designation C/2017 U1, suggesting it was a comet. But within days, as more observations poured in, astronomers realized they were dealing with something unprecedented. No coma of gas and dust surrounded this object. The telltale signature of a comet was completely absent. The reclassification came swiftly. C/2017 U1 became a /2017 U1, marking it as an asteroid. But even this designation proved inadequate when orbital calculations revealed the object's true nature. It was moving too fast to be gravitationally bound to our sun. This visitor was an interloper, a wanderer from the depths of interstellar space. The International Astronomical Union faced an unusual problem. They needed to create an entirely new classification system. Thus was born the I designation for interstellar objects, and our mysterious visitor became 1I/2017 U1. But it needed a name worthy of its historic status. Hawaiian astronomers suggested Oumuamua, meaning scout or first distant messenger from the past. The name proved prophetic in ways no one could have anticipated. The cosmic messenger's strange properties. As Oumuamua tumbled through our solar system, each observation revealed new puzzles. The object stretched between 100 and 1,000 meters in length, but its exact shape remained elusive. Its brightness varied dramatically over a 7-hour rotation period, suggesting an extremely elongated form, perhaps 10 times longer than it was wide. Some scientists envisioned a cosmic cigar, while others proposed a flattened disk spinning like a celestial frisbee. The object's unusual geometry wasn't its only peculiarity. Unlike the dark, carbon-rich surfaces typical of asteroids, Oumuamua reflected light with surprising efficiency, at least 10 times brighter than expected for a conventional space rock. This metallic sheen added another layer to the mystery. What kind of natural process could create such a highly reflective interstellar wanderer? But Oumuamua's origin story presented perhaps the greatest puzzle. As an asteroid-like object, it must have formed in the inner regions of its home planetary system, where rocky materials could condense from the stellar nebula. Yet how did it escape its birthplace to begin the long journey through interstellar space? Conventional wisdom suggested that massive collisions or gravitational encounters with giant planets could eject such objects, but the energy requirements seemed staggering. Some researchers proposed an alternative. Perhaps Oumuamua was actually a comet in disguise. After millions or billions of years traveling through the frigid interstellar medium, its surface could have become so heavily irradiated and dust-coated that the volatile ices underneath remained hidden. When the sun's warmth reached this cosmic traveler, the surface layers might have prevented any visible outgassing, creating the appearance of an asteroid while retaining a comet's internal composition. The acceleration that broke physics. What truly set Oumuamua apart from every other celestial object wasn't its mysterious shape or reflective surface. It was what happened as the object rounded the sun and began its journey back into interstellar space. On September 9, 2017, Oumuamua reached perihelion, its closest approach to our star, screaming past at a mind-bending 87 kilometers per second. According to every law of physics, what happened next was impossible. As Oumuamua departed our solar system, it should have followed a predictable path, gradually slowing as the sun's gravity pulled against its motion. Instead, something gave it a push. The object accelerated away from the sun with a non-gravitational force that defied explanation. The acceleration was subtle, only about 17 meters per second squared at its peak, but it was undeniably real and utterly baffling. Robert Warwick, credited with Oumuamua's discovery, stated definitively that the object's motion could not be explained by any known physics governing normal asteroids or comets. This wasn't a measurement error or observational glitch. Multiple independent observations confirmed the anomalous acceleration over several months as Oumuamua continued deviating from its predicted trajectory. In physics, objects only accelerate when forces act upon them. Scientists desperately searched for explanations. Solar radiation pressure, the gentle push of photons from the sun, could theoretically provide such a force, but the effect would be far too weak to explain Oumuamua's behavior, assuming it had the density and composition of a typical asteroid. Researchers then considered whether Oumuamua might be outgassing like a comet, creating a rocket-like thrust as sublimating ice propelled material away from its surface. But the Spitzer Space Telescope spent 30 hours studying the object in infrared wavelengths and detected absolutely nothing. No gas, no dust, no thermal signature that would indicate active sublimation. For comparison, typical comets create easily detectable comas and tails that Spitzer routinely observes. The absence of any detectable outgassing eliminated the most obvious explanation for the acceleration. Whatever was pushing Oumuamua remained completely invisible to our most sensitive instruments. The Harvard hypothesis: could it be alien technology? Into this scientific vacuum stepped Dr. Avi Loeb, chairman of Harvard University's astronomy department and one of the most respected astrophysicists in the world. In 2018, Loeb co-authored a paper that sent shockwaves through the scientific community and captured headlines worldwide. His proposal was as elegant as it was controversial. Oumuamua might represent humanity's first encounter with alien technology. Loeb's argument hinged on a radical reinterpretation of Oumuamua's physical properties. If the object wasn't a typical space rock, but rather an extremely thin sheet of material, perhaps only 0.3 to 0.9 millimeters thick, then solar radiation pressure could indeed account for the observed acceleration. Such an object would have an enormous surface area relative to its mass, making it extraordinarily sensitive to the gentle push of starlight. But nature doesn't spontaneously create kilometer-scale objects that are thinner than a sheet of paper. Such extreme geometry would require artificial construction, specifically the kind of lightweight sail that an advanced civilization might use to harness stellar radiation for interstellar travel. Loeb proposed that Oumuamua was essentially a cosmic billboard, a light sail deliberately engineered to catch starlight and use it for propulsion across the vast distances between stars. The light sail hypothesis explained not only Oumuamua's anomalous acceleration but also its unusual reflectivity and lack of detectable outgassing. An artificial structure could maintain its integrity and surface properties throughout the long journey through interstellar space, arriving in our solar system with its technological functionality intact. Loeb's suggestion met fierce resistance from much of the astronomical community. The extraordinary claims demanded extraordinary evidence, and many researchers felt that invoking alien technology was premature when more conventional explanations might still be found. The debate grew heated as Loeb continued advocating for his hypothesis through multiple papers and public presentations, arguing that the scientific community's reluctance to consider artificial origins reflected a form of intellectual conservatism rather than rigorous skepticism. The dark comet theory, nature's invisible thruster. While Loeb championed the alien technology hypothesis, other researchers pursued more conventional explanations for Oumuamua's strange behavior. Dr. Daryl Seligman, a postdoctoral researcher at Cornell University, emerged as the leading advocate for a natural explanation that could account for the object's acceleration without invoking extraterrestrial engineering. In 2020, Seligman proposed that Oumuamua was indeed outgassing, but the expelled material was completely invisible to our telescopes. Instead of the water vapor, carbon dioxide, and dust typically ejected by comets, Oumuamua might be releasing pure hydrogen gas, a substance essentially undetectable by the infrared instruments that observed the object. Seligman's initial proposal suggested that Oumuamua was a hydrogen iceberg, a chunk of frozen hydrogen that sublimated as it approached the sun, creating the rocket-like thrust that explained the observed acceleration. This hypothesis elegantly resolved the apparent contradiction between visible acceleration and invisible outgassing. However, Loeb quickly countered with mathematical calculations showing that hydrogen icebergs couldn't survive the journey through interstellar space. The faint but pervasive radiation from distant stars would provide enough energy to sublimate any hydrogen ice long before it reached our solar system. Even objects originating in the nearest and densest molecular clouds would arrive as vapor rather than solid material. Faced with this critique, Seligman temporarily abandoned the hydrogen iceberg model, but continued exploring how hydrogen gas might explain Oumuamua's behavior. The breakthrough came in 2023 through collaboration with Dr. Jennifer Bergner, an assistant professor at the University of California, who brought crucial laboratory expertise to the puzzle. Bergner's research had demonstrated that water ice subjected to radiation in extremely cold conditions could trap molecular hydrogen within its crystalline structure. When this ice later warmed, say during a close encounter with a star, the trapped hydrogen could be released as the crystal lattice rearranged itself. This process required no surface melting or visible outgassing, making it essentially undetectable to conventional astronomical observations. The beauty of this mechanism lay in its ubiquity. Water ice is abundant throughout the galaxy, and cosmic radiation provides the energy source needed to create hydrogen-trapping structures. Any comet-like object traveling through interstellar space for millions of years would naturally accumulate trapped hydrogen, creating a reservoir of invisible propellant that could be released during stellar encounters. Seligman and Bergner proposed that Oumuamua represented an entirely new category of object, a dark comet with an invisible coma consisting purely of hydrogen gas. This classification explained both the acceleration and the lack of detectable outgassing while requiring no exotic physics or alien technology. The discovery of Earth's dark comets. If Oumuamua truly represented a dark comet powered by invisible hydrogen outgassing, Seligman reasoned, similar objects might exist closer to home. Perhaps the solar system harbored its own population of dark comets, objects that appeared asteroidal but exhibited subtle acceleration that couldn't be explained by known forces. The search through existing astronomical databases proved remarkably fruitful. Seligman, Bergner, and their collaborators identified 6 objects within our solar system that matched their criteria. Small, asteroid-like bodies exhibiting non-gravitational acceleration that couldn't be attributed to solar radiation pressure or detectable outgassing. These potential dark comets shared several characteristics. They were all relatively small, some as tiny as 3 meters across, and appeared completely unremarkable in telescopic observations. All belonged to the near-Earth object population, orbiting close enough to our planet that spacecraft missions would be technically feasible. Most importantly, all showed signs of subtle but persistent acceleration that defied conventional explanation. The accelerations were minimal, far too small to suggest the objects were zipping around the solar system like alien spacecraft. Instead, they exhibited the kind of gentle, persistent thrust that might result from slow hydrogen outgassing as trapped gas gradually escaped from warming ice structures. One of these potential dark comets, designated 1998 KY26, was already scheduled for a close encounter with human technology. The Japanese Hayabusa 2 probe, having successfully completed its primary mission to asteroid Ryugu, received a mission extension to visit this small, rapidly rotating object in 2031. The flyby could provide crucial data about whether 1998 KY26 exhibits the hydrogen outgassing predicted by the dark comet theory. The discovery of multiple dark comet candidates within our solar system provided strong support for Seligman's hypothesis. If such objects existed locally, it seemed reasonable that Oumuamua might represent an interstellar example of the same phenomenon. The dark comet theory offered a natural explanation for the mysterious visitor without requiring exotic physics or alien technology. Other interstellar wanderers. While Oumuamua captured the world's attention as our first confirmed interstellar visitor, it wasn't destined to remain unique for long. In August 2019, amateur astronomer Gennady Borisov discovered what would become our second confirmed interstellar object, designated 2I/Borisov in honor of its discoverer. Unlike its enigmatic predecessor, Borisov behaved exactly as astronomers expected an interstellar comet should behave. As it approached the inner solar system, it developed a spectacular coma and tail spanning nearly 14 Earth diameters. Though invisible to the naked eye due to its distance, closest approach occurred beyond Mars's orbit. Telescopic observations revealed a classic comet displaying all the traditional signatures of outgassing. Borisov's composition, while somewhat unusual, fell within the range of known cometary materials. Its roughly half-kilometer diameter made it similar in size to Oumuamua, but its conventional behavior provided a stark contrast to the mysterious acceleration that had baffled astronomers studying the first interstellar visitor. After perihelion, Borisov began fragmenting, a common fate for comets of this size passing through the inner solar system. The breakup provided additional insights into the object's internal structure and composition, confirming its status as a relatively normal comet that happened to originate beyond our solar system. The discovery of Borisov validated theoretical predictions about interstellar objects while highlighting just how unusual Oumuamua's properties really were. If most interstellar visitors behaved like Borisov, what made Oumuamua so different? Captured visitors and retrograde rebels. Not all interstellar objects pass through the solar system as brief visitors. Some become permanent residents, captured by gravitational interactions with the giant planets, particularly Jupiter, whose massive gravitational field can slow incoming objects enough to bind them into solar orbits. Several comets in our system may represent such captured interstellar wanderers. Machholz 1 and Hyakutake, C/1996b2, exhibit orbital characteristics and compositions that suggest extrasolar origins. Their highly elliptical orbits and unusual chemical signatures distinguish them from typical solar system comets, making them prime candidates for objects that once wandered between the stars. These captured visitors offer unique scientific opportunities. Unlike brief flyby encounters such as Oumuamua and Borisov, captured objects remain accessible for detailed study over multiple orbital periods. Future missions could potentially sample these cosmic immigrants directly, providing unprecedented insights into conditions in other planetary systems. Perhaps the most intriguing captured object is 514,107 Oumuamua, an asteroid locked in a 1:1 orbital resonance with Jupiter while traveling in retrograde motion, opposite to the direction of planetary orbits. This backward trajectory strongly suggests interstellar origins, as it's extremely difficult to explain how a native solar system object could acquire such motion. Oumuamua's asteroid classification makes it particularly interesting. Most interstellar objects are expected to be comets, as icy bodies are more easily ejected from their birth systems. The presence of a captured interstellar asteroid suggests either that rocky objects can also be ejected in significant numbers, or that this object was once a comet whose volatile materials have long since been depleted. If Oumuamua was captured early in solar system history, when Jupiter was still migrating and the planetary configuration was more dynamic, it could represent a fossil from our cosmic neighborhood's youth. A 4.5 billion-year-old messenger from a nearby star system that has since evolved beyond recognition. Tracking the messenger's origins. Determining where Oumuamua originated required astronomical detective work spanning millions of years and vast cosmic distances. By carefully tracing the object's trajectory backward through space and time, astronomers attempted to identify its birth system among the hundreds of billions of stars in our galactic neighborhood. The investigation revealed that Oumuamua approached our solar system from the direction of Vega, the brilliant star in the constellation Lyra. However, this apparent origin proved misleading. Vega's current position doesn't represent where it was located millions of years ago when Oumuamua began its interstellar journey. Accounting for stellar motion over cosmic timescales, researchers identified 4 possible home stars that could have ejected Oumuamua in our direction. These candidate systems lay between a few dozen and 81 light-years from Earth, relatively close neighbors in galactic terms, but still representing journeys of millions to tens of millions of years for the wandering object. The uncertainty in Oumuamua's origin story reflects the challenges of interstellar archaeology. Stars move through the galaxy in complex orbits, occasionally coming close enough to influence each other's planetary systems. The gravitational dance of stellar encounters can eject comets and asteroids at velocities sufficient for interstellar travel, but tracking these ancient interactions requires precise knowledge of stellar positions and velocities over vast time periods. Even with modern astronomical databases and sophisticated computer modeling, definitive identification of Oumuamua's home system may remain elusive. The object's true birthplace could be a star that has since moved far from its original position, or it might have been ejected so long ago that its trail has become hopelessly confused by multiple gravitational encounters. The chase, mission to catch a cosmic visitor. By the time astronomers recognized Oumuamua's true nature, the object was already racing away from the inner solar system at tremendous speed. We had missed our chance for close-up study, or had we? Some researchers began contemplating what seemed impossible, launching a mission to chase down and rendezvous with humanity's first confirmed interstellar visitor. The challenges were formidable. Oumuamua was already more than 6 billion kilometers from Earth and traveling at 26 kilometers per second, faster than any spacecraft humans have ever built. No chemical rocket system could achieve the velocity needed to catch up with the receding object, much less slow down enough for meaningful scientific observations. However, the laws of orbital mechanics offered potential solutions through clever mission design and gravitational assists from the giant planets. Project Lyra, launched by the Initiative for Interstellar Studies, developed detailed proposals for intercepting Oumuamua using gravity-assist trajectories that could accelerate spacecraft to the necessary velocities. The most ambitious proposal involved a complex multi-stage trajectory beginning with a launch toward Jupiter. The spacecraft would use Jupiter's gravity to slow down and fall toward the Sun, then ignite its engines during closest solar approach to achieve maximum acceleration through a solar Oberth maneuver. This technique could theoretically propel a probe to over 70 kilometers per second, fast enough to eventually overtake Oumuamua in interstellar space. However, this approach required technology at the limits of current capability. The close solar encounter would demand heat shielding similar to that used by the Parker Solar Probe, adding 72 kilograms to the spacecraft mass and constraining payload capacity. The complex trajectory would also require maneuvers never before attempted in actual space missions, increasing technical risks significantly. An alternative approach proposed by Project Lyra involved a more conservative trajectory using multiple Earth and Venus gravity assists, followed by a final Jupiter encounter to accelerate the spacecraft toward Oumuamua. This profile would achieve lower final velocity but require no heat shielding and use only proven orbital mechanics techniques. Mission planners identified launch windows between 2030 and 2033 that could result in Oumuamua encounters around 2048. While the journey time seemed daunting, researchers pointed out that even a century from now, Oumuamua would still be far closer than any confirmed exoplanet, making it potentially humanity's most accessible target for interstellar exploration. The future of interstellar object detection. While pursuing Oumuamua might answer questions about our first interstellar visitor, a better strategy might involve preparing for future arrivals. NASA estimates that interstellar objects pass through the inner solar system roughly once per year, but their small size and high velocity make detection extremely challenging with current technology. The Vera C. Rubin Observatory, scheduled to begin operations in late 2025, promises to revolutionize interstellar object detection. This powerful survey telescope will scan the entire visible sky every few nights, identifying moving objects with unprecedented sensitivity. Most importantly, it should detect interstellar visitors up to 3 months before they reach closest approach to the Sun, providing adequate time for detailed observations and potentially even rapid response space missions. The Rubin Observatory's legacy survey of space and time will create a database of millions of astronomical images spanning a full decade of observations. This comprehensive dataset will be ideal for identifying subtle changes in the night sky, including the trajectories of comets, asteroids, and interstellar interlopers. Preliminary estimates suggest the survey could discover up to 70 Oumuamua-like objects annually once fully operational. The European Space Agency's Comet Interceptor mission, scheduled for launch in 2029, represents another innovative approach to studying these elusive visitors. Rather than targeting a specific object, the mission will park a probe at the L2 Lagrange point for up to 3 years, waiting for a suitable comet or interstellar object to appear. When a target is identified, the spacecraft will spring into action, conducting a high-speed flyby to create detailed three-dimensional maps of the visitor. This mission concept acknowledges the fundamental unpredictability of interstellar object arrivals while positioning humanity to respond rapidly when opportunities arise. The Comet Interceptor will become the first space mission launched with an unknown target, representing a new paradigm for exploration of transient cosmic phenomena. The economics of cosmic curiosity. The technical feasibility of chasing Oumuamua or waiting for future interstellar visitors raises profound questions about the allocation of scientific resources. Space missions require enormous investments of money, time, materials, and intellectual capital. Is satisfying our curiosity about Oumuamua worth the costs involved? Proponents argue that humanity's first confirmed interstellar visitor represents a unique scientific opportunity that may not be repeated for decades or centuries. The questions surrounding Oumuamua's nature, whether it represents advanced alien technology, a new category of natural object, or something else entirely, have implications that extend far beyond astronomy into physics, astrobiology, and our understanding of intelligence in the universe. The investment required for an Oumuamua intercept mission would likely cost billions of dollars and require international cooperation on a scale similar to major space stations or Mars exploration programs. Such expenditures must compete with numerous other scientific priorities, from climate research to medical advances to fundamental physics experiments. However, the potential payoff could be transformational. If Oumuamua truly represents alien technology, confirming this would constitute the most important discovery in human history, fundamentally altering our understanding of our place in the cosmos. Even if it proves to be a natural phenomenon, detailed study could reveal new physics or demonstrate novel mechanisms for interstellar transport of material between star systems. The debate over Oumuamua missions ultimately reflects deeper questions about the value of pure scientific research and humanity's commitment to understanding the universe. Some argue that the costs of interstellar exploration are premature when pressing terrestrial problems demand attention. Others contend that expanding human knowledge and capability represents an investment in our species' long-term survival and prosperity. The theoretical battlefield. As Oumuamua recedes beyond the reach of our telescopes, the scientific debate over its nature continues with undiminished intensity. The conflict between Loeb's alien technology hypothesis and Seligman's dark comet theory reflects broader tensions within the scientific community about appropriate standards of evidence and the role of speculation in advancing knowledge. Loeb's advocacy for considering artificial origins has drawn criticism from colleagues who argue that extraordinary claims require extraordinary evidence. Many astronomers feel that invoking alien technology is premature when natural explanations remain plausible, even if incomplete. The resistance partly reflects scientific culture's emphasis on parsimony, the principle that simpler explanations are generally preferable to complex ones. However, Loeb counters that scientific conservatism can become an obstacle to discovery. He argues that the astronomical community's reluctance to seriously consider artificial origins reflects sociological rather than scientific factors. The stigma associated with UFO research and the fear of professional ridicule may prevent rigorous investigation of genuinely anomalous phenomena. The dark comet theory has gained support as additional objects exhibiting similar acceleration have been identified within our solar system. The upcoming Hayabusa 2 encounter with 1998 KY26 could provide crucial evidence for or against hydrogen outgassing as an explanation for non-gravitational acceleration. If the Japanese probe detects signs of invisible outgassing, it would strongly support Seligman's hypothesis. Yet even confirmation of the dark comet mechanism wouldn't definitively resolve Oumuamua's nature. The object might represent a hybrid phenomenon, natural materials arranged in an artificial configuration, or technology designed to mimic natural objects. The binary choice between natural and artificial may prove overly simplistic for truly novel phenomena. Implications for astrobiology. The Oumuamua controversy has profound implications for the search for extraterrestrial intelligence, SETI, and our expectations about how we might first encounter alien technology. Traditional SETI focuses on detecting deliberate communication signals, radio transmissions, or optical beacons designed to attract attention across interstellar distances. The possibility that Oumuamua represents alien technology suggests an alternative detection scenario: accidental encounter with artifacts not intended for communication. Such objects might be interstellar probes conducting reconnaissance, failed or abandoned missions drifting through space, or even debris from technological civilizations. This paradigm shift has led some researchers to advocate for expanded SETI strategies that include systematic searches for artificial objects within our solar system. Rather than listening for signals from distant stars, we might find evidence of alien intelligence much closer to home, perhaps in objects we initially dismiss as natural phenomena. The debate also highlights the challenges of recognizing alien technology when we encounter it. Our expectations about extraterrestrial artifacts are inevitably shaped by human technological development, but truly advanced civilizations might employ principles and materials completely foreign to our experience. What appears to violate known physics might actually demonstrate unknown physics, making the distinction between impossible and merely unfamiliar extremely difficult. The cascade of discovery. Regardless of Oumuamua's ultimate nature, its discovery has already transformed our understanding of interstellar space and the objects that traverse it. The mere existence of detectable interstellar visitors confirms theoretical predictions about the ejection and capture of material during planetary system formation and evolution. The observation that at least some interstellar objects exhibit unusual properties, whether through dark comet outgassing or more exotic mechanisms, suggests that the space between stars may be far more dynamic and interesting than previously imagined. Instead of cold, empty vacuum punctuated by occasional dead rocks, interstellar space might teem with active objects undergoing complex physical and chemical processes during their million-year journeys. The discovery of potential dark comets within our solar system represents an equally significant finding. If confirmed, these objects would constitute an entirely new class of solar system bodies with important implications for planetary defense, resource utilization, and our understanding of small body evolution. Objects that appear asteroidal but contain significant water ice could serve as waypoints for future interplanetary missions while posing unexpected impact risks if their acceleration properties aren't properly understood. Looking forward, the next interstellar messenger. As we await the next confirmed interstellar visitor, the lessons learned from Oumuamua continue shaping astronomical practice and theoretical frameworks. The object's rapid discovery to escape timeline demonstrated the need for responsive observation networks capable of rapidly characterizing transient phenomena. Future interstellar object detections will benefit from improved survey capabilities, more sensitive instruments, and better theoretical understanding of what to expect. The Rubin Observatory's systematic sky monitoring should provide sufficient advance warning for detailed spectroscopic observations, thermal measurements, and even rapid response space missions. The development of standing protocols for interstellar object investigation will ensure that future visitors receive more comprehensive study than Oumuamua. International coordination of ground-based and space-based assets could maximize the scientific return from brief observation windows, while prepositioned spacecraft like the Comet Interceptor could provide close-up data impossible to obtain from Earth-based observations alone. The philosophy of cosmic encounters. Beyond its scientific implications, Oumuamua has forced humanity to confront fundamental questions about our expectations for first contact with alien intelligence. The possibility that we might have already encountered extraterrestrial technology and failed to recognize it definitively challenges assumptions about how such discoveries would unfold. Science fiction often portrays first contact as an unambiguous event, clearly artificial spacecraft arriving with obvious technological signatures or deliberate communication attempts. The Oumuamua experience suggests that reality might be far more subtle and ambiguous. Our first glimpse of alien intelligence might come through objects that could equally well be natural phenomena, forcing us to grapple with uncertainty and incomplete information. This ambiguity reflects deeper philosophical questions about the nature of intelligence and technology. Advanced civilizations might employ principles so sophisticated that their artifacts appear indistinguishable from natural objects to less developed observers. Arthur C. Clarke's famous observation that any sufficiently advanced technology is indistinguishable from magic might equally apply to distinguishing it from nature. The endless frontier. As Oumuamua continues its journey into the cosmic dark, now more than 6 billion kilometers from Earth and receding at 26 kilometers per second, it carries with it answers we may never obtain. Whether alien technology, dark comet, or something else entirely, our first confirmed interstellar visitor has already achieved something remarkable. It has reminded us that the universe still holds surprises capable of challenging our deepest assumptions about reality. The ongoing debate over Oumuamua's nature embodies the best traditions of scientific inquiry. Rigorous analysis, creative hypothesis formation, and willingness to follow evidence wherever it leads, even into uncomfortable territory. Whether Loeb's alien technology hypothesis or Seligman's dark comet theory ultimately proves correct matters less than the quality of investigation they inspire. Perhaps most importantly, Oumuamua has demonstrated that we live in a universe where interstellar exchange of materials and possibly information occurs on a regular basis. Our solar system is not an isolated island, but a way station in a vast network of cosmic traffic flowing between the stars. Every year brings new visitors from distant systems, each carrying its own secrets about conditions and processes in alien worlds. The technology to detect and study these visitors continues improving rapidly. Within a decade, we may be discovering dozens of interstellar objects annually and routinely sending spacecraft to investigate the most intriguing specimens. The Oumuamua mystery may soon be resolved not through theoretical debate, but through direct examination of similar objects under controlled conditions. Until then, Oumuamua serves as a humbling reminder of how much we still don't know about the cosmos and our place within it. Somewhere in the space between stars, our first confirmed interstellar visitor continues its ancient journey, carrying secrets that may forever remain locked in the cosmic dark. Its brief passage through our solar system opened a window into the vast unknown, revealing possibilities we had never imagined and questions we had never thought to ask. The universe, it seems, still has the power to surprise us. In a cosmos filled with dark matter and dark energy, perhaps it's fitting that our first interstellar visitor should introduce us to the possibility of dark comets, objects that defy easy categorization and challenge our understanding of the boundary between the natural and the artificial, the familiar and the alien. As we prepare for the next interstellar messenger, Oumuamua's legacy continues shaping our expectations and capabilities. Whether scout, wanderer, or something else entirely, it has already fulfilled its Hawaiian name's prophecy, serving as a distant messenger that has forever changed our perspective on the cosmos and our place within its infinite mystery. The search for answers continues, carried forward by human curiosity and technological capability. Somewhere among the stars, other interstellar wanderers are already en route to our solar system, each carrying its own secrets and surprises. When they arrive, we'll be better prepared to unravel their mysteries, Thanks to the lessons learned from our first cosmic visitor that dared to defy the laws of physics and challenge our understanding of what's possible in the vast, dark space between the stars.